effortless vertical transport. A seamless journey between floors. But behind these simple doors and hidden within this metal box lies a masterpiece of engineering. So, how does it all work? Let's find out. It's a precisely balanced system, working in perfect harmony. Turns a sheave, which grips a set of high-tensile steel ropes. These ropes connect the elevator car to a crucial component, the counterweight. To understand how these parts work together, let's break them down, starting with the most familiar component, the elevator car. This is the cabin that carries passengers and goods, forming a protective enclosure. Its doors, synchronized with the landing doors at each floor, are critical for ensuring safe entry and exit. The interior itself is designed for safety, comfort, and durability, providing a secure space for transit. But the car is more than just a box. It's a precisely engineered frame designed to move smoothly. This structure is the elevator shaft, or hoistway, the vertical path through which the car travels. But to ensure a perfectly smooth and stable ride, the car doesn't just float. It's guided. Fixed to the walls of the shaft are steel guide rails, providing a rigid, unwavering path from the bottom floor to the top. And attached to the car itself are guide shoes, which slot perfectly around the rails.
With this foundation in place, we can now explore the systems that power the movement.
An elevator car, even when empty, can weigh several tons. Lifting it efficiently requires a clever solution. At the very top, we find the heart of the operation, the traction system. A powerful electric motor turns this large, grooved wheel, called a sheave. The hoist cables pass over it.
Think of it like a seesaw. With the car and counterweight nearly balanced, the motor only needs to lift the small difference in weight. The car and counterweight are nearly equal in mass. The motor doesn't lift the full load.
It only needs to overcome friction and the small difference in weight. It is this simple, yet ingenious, principle of balancing that makes modern elevators both practical and sustainable. Together, these two parts form the traction system, responsible for converting electrical energy into the mechanical force that moves the elevator. This wheel is called the traction sheave. It doesn't wind the cables like a winch. Instead, it uses a simple yet brilliant principle. This creates immense friction, or traction, allowing the sheave to grip the cables. As the sheave turns, this creates immense friction, or traction, allowing the sheave to grip the cables. As the sheave turns, the magic of this system isn't just power, it's grip. This is achieved through a principle called traction. And that is the traction system, a simple yet brilliant solution that makes the modern elevator possible. Every press of a call button, whether on a landing or inside the car, sends a digital signal, a request for service. But it doesn't just create a simple queue. The controller uses complex algorithms. The system dispatches the car along the most efficient path, servicing calls in a logical sequence to minimize travel and wait times. Inside, weighted arms are held in place by springs. But when the speed reaches a preset, dangerous limit, it activates the most critical safety feature, the emergency brakes. These aren't like the brakes in your car. They are powerful, wedge-shaped blocks of metal designed to bite into the steel guide rails. And even if every other system were to fail, there's one last line of defense at the very bottom of the shaft: the buffers. They are designed to absorb the kinetic energy of a descending car. Individually, they are marvels of engineering. But together, they create a symphony of vertical motion. And watching over it all, the ever-vigilant safety systems, ensuring every journey is a secure one.